Advanced Algebra Chapter 8, Lesson 4, continuing to look at logarithms. And again, you're going to see the pre-calculus lesson number on the video, but this is the Advanced Algebra series. We're going to look in this section about how to evaluate logarithms, and I'm also going to talk about natural logarithms in this video. Now, natural logarithms aren't until Chapter 8, Lesson 6 of Advanced Algebra, but I'm going to talk about them in this video, so pay attention to that. And really, I can summarize it in saying that everything you learn about logarithms, natural logarithms, is simply a base E number. In other words, the B value that we substitute in is the base number E, and E is a calculus number. It's an irrational number like pi. Its decimal equivalent never repeats and never terminates, but it has some very interesting properties that allow it to be used as a base number in a number of calculus types of problems and in financial types problems, and we'll look at those in Chapter 8, Lesson 6. But pay attention to that as I'm discussing it in this video, because we will use it in Chapter 8, Lesson 6. Chapter 3, Lesson 3, Precalculus, continuing our discussion of logarithmic functions. In this video, we want to take a look at common logarithms, and we'll look at natural logarithms, and then we'll look at evaluating these logarithmic expressions that we've been speaking about. Common logarithms are known as base 10 logarithms. So you remember from our discussion previously that y, which is an exponent, log of a base b produces the value of x. Common logarithms are simply a logarithm where this b value is a 10. So any logarithm that has a b value or a base of 10 is known as a common logarithm. This is connection to, or has connections to, our base 10 numbering system and metric system and scientific notation. So it's a very valuable and very useful logarithm, and it's the one we'll use most often when we're looking at applying it to problems. We can drop the subscript, and in doing so we understand that the base is 10, meaning this: I can take the logarithmic expression log base 10 of 100, okay, and I can rewrite it without writing this base number, and if I do that, then the base 10 is understood. In other words, we understand that there's a 10 here even though it's not written. So anytime you see an expression where there is no base and you have the word logarithm, we understand that it's base 10. And on our calculator, this is the log key. So when you use the log key on your calculator, that is going to be using a base 10 logarithmic expression. Okay, so that's the common log. The next one we want to look at is the natural log. The natural logarithm, much like the common logarithm, is simply a logarithm that has the same base. So if we take our logarithmic expression that we've been talking about, where b is the base, if this b is the number e, then it's known as a natural logarithm. E is a number. It's an irrational number like pi. Its decimal never repeats and never ends. So it's irrational, but it is a number. It remains constant. And the number e has some special calculus properties which allow it to be used in many, many different situations. So it's a very valuable number that we use. And again, we can rewrite it using the abbreviation ln, and if we do that, then we understand the base to be an e. In other words, we just talked about earlier where if I was to write this expression and I was not to write a base here, we understand that this is a 10. 10 to some power gives me this x. If we see an expression where we have the letters ln and there's no base written here, we understand that the base here is the number e. Okay, so this is known as the natural log. So this is a common logarithm, base 10. This is a natural logarithm, base e. And on our calculators, we do have an ln key, so we would use that if we were using our calculator to evaluate some kind of expression that had a natural log in it. So those are the two bases that you need to be aware of: the common logarithm where the base 10 and the 10 is understood, and the natural logarithm where the base is e, and when you see the expression ln, we know that it's natural log and that the base is e. So let's take a look now at how we can evaluate these logarithmic expressions that we've been talking about. So evaluate the logarithmic expression without using a calculator. We talked about earlier that the reason we went to logarithms, or one of the ways we want to think about logarithms is that the logarithm is the inverse operation of the exponential, and the exponential is the inverse of the logarithm. So much like when we have a expression 3 times x equals 6 and we want to solve it, we do the inverse, and division undoes multiplication. We want to do that here. We have a logarithmic expression and we're asked to evaluate it, so we want to change it into its exponential because the exponential will undo the logarithm. So what is the exponential equivalent of this, or how do we change this into an exponential expression? Well, remember I talked about what this word means, or what logarithm, how I wanted you to think about it, is a question. What's the exponent of 4? So what's the exponent of 4 that will give me this number here, 4? So what's the exponent of 4 that will give me 4? So we change it from its logarithmic expression into an exponential. Now that it's in exponential form, we can work to solve this. Now this is a 4 to the 1, and so what you want to understand here is this. If the bases are the same, if the bases are equal, which they are here, then the exponents must also be equal. Okay, so if the bases are equal, then the exponents are equal. And so here is my answer to this expression, or I have evaluated this logarithmic expression. So let's evaluate this expression. And again, what does log mean? What is the exponent of 2? What is the exponent of 2 that will equal 32? So that's the first step. We change it from its logarithmic form into its exponential, inverse operation, so to speak. Now, I said that the bases need to be the same, because if the bases were equal, then the exponents would be equal. And you'll notice in this case, the bases are not equal. The bases are not the same. This is a 2, so this is a 32. So what we need to do in this situation, again, is to make this into a base of 2 then. Again, one of the things we do in math all the time is if it's not in a form we like it, we do something that mathematical that puts it in the form that we want it. So I need to change 32 into a base 2. In other words, 2 to some power can give me 32. So 2 to the 5th power I know is 32. 2 times 2 times 2 times 2 times 2 is 32. So instead of 32, I can rewrite this with this base of 2 to the 5th. Now you'll notice that my bases are equal. And as I said, if the bases are equal, then the exponents must also be equal. So we want to change it from its logarithmic to exponential. We then want to change it so the bases are the same, and if the bases are equal, then the exponents would be equal, so y would be 5 in this case. All right? Let's do another example. Let's do this one below. So let's take a look at this one here, and again, evaluate this without a calculator. So again, log base 5. So what does that mean? What is the exponent of 5 that will give me this expression here? Now again, you'll notice that these bases are not the same. This is a base 5, and this is some kind of weird thing over here. So again, we need to go back and change it into a base 5. So we have to remember a couple of things. First thing I want to do when I have a square root is to change this into its exponential form. Okay? In other words, you remember that this would be 25 to the 1/3 power. You remember that a root can be changed to a fractional exponent where the denominator is the index and this is the power of this number. Now again, I still don't have a base 5. I have 25 to the 1/3. But I can change 25 into 5 squared. So I have 5 squared to the 1/3. 5 squared is 25. 25 to the 1/3 is cube root of 25. So I haven't changed it. So now when I have a power raised to a power, I can simplify that by multiplying those together. So this would be 5 to the 2/3. So I can change this then into the same base where this is a base 5 and this would be 5 to the 2/3. Now again, because my bases are equal, then my exponents must be equal as well, so this evaluated would be 2/3. Okay, so again, step process. Exponential form, which is the inverse of logarithm. Change the bases so that they're equal, and if the bases are equal, then the exponents will be equal. Let's do a couple more examples here, and then we'll wrap this up. Alright, so in this example, we have log base 6 of this value here. So again, what does this mean? To evaluate this means to change it into exponential, so I want to do that first. What is the exponent of 6 that will give me this expression here? Now again, I need the same base, and you can tell that these are not the same bases, so this one is going to need to be changed into a base 6. So I've got to do a couple things here. First of all, I'm going to change this root into a fractional exponent, 1/5. I know I'm going to need a base 6. 36 I can change into 6 squared, so that's 36 to the 1/5. Then I'm going to bring this up here. So I have 1 over 6 to the 2/5. Okay, changing that, multiplying these exponents. Now, it's still not the same base because the 6 is in the denominator, but I can move the 6 into the numerator, and remember that changes the sign of the exponent. So I can do all of that algebraic manipulation. So I'm going to bring this over here. So 6 to what power will give me 6 to the negative 2/5 power. So I've made the bases the same, so because the bases are equal, the exponents must be equal. So this would be negative 2/5. Alright, let me do one more example that you'll might run into, and then we'll wrap this up. Okay, let me go back up. I think it's up here. Oh yeah, here it is. Alright, so here I have, let's evaluate this one here. So again, we change it to exponential first. So what is the exponent of 6 that will give me 1? So again, I need to have the same bases. Now, I can't change 1, or how do I change 1 into a base 6? I need to have 6, but I need it to be equivalent to 1. So 6 to what power is 1? Well, 6 to the 0 power is 1, because anything to the 0 power is 1. So 6 to the y is going to be equal to 6 to the 0. So again, because the bases are equal, then the exponents must be equal. So in this case, y would be 0. So to evaluate logarithmic expressions, again, you change it to its exponential form. Then if the bases are equal, then the exponents must be equal. And you may need to do some algebraic manipulation of these things in order to get the bases equal, but once they're equal, then you can evaluate the logarithm because the exponents will be equal as well.